In this problem, we are given a group G of permutations on a set X. First thing to notice is there's nothing said about what X is. X might be a finite set. That's the most typical kind of thing we think of with permutations, but it could be an infinite set. X could be infinite. G could be infinite. There's nothing about whether G is a finite group or not. In either context, whether X is infinite or not, we can define this set stab A, which stands for the stabilizer of A. Stabilizer of A, where A is an element of X. X is not necessarily a group. It's just a set. Typically, it's a set of numbers, but it could be a set of people. It could be a set of buildings. It could be a set of planets, stars in the galaxy. Okay, X could be anything. A is just an element of X. The stabilizer, though, is a subset of G. It's the collection of elements alpha of G. Alpha is a permutation of X, a one-to-one and onto function from X to itself, satisfying the property that alpha maps A to itself. It stabilizes A, keeps it fixed. A, but not necessarily other elements in X. Prove the stabilizer of A is a subgroup of G. Evidently, we can create one stabilizer for each element of X. There could be infinitely many different stabilizers that are infinitely many different subgroups of G if X happens to be an infinite set. How do you prove this? I hope you remember we want to use a subgroup test. Don't use the finite subgroup test because there's nothing about G being finite. You'd have to use the one-step subgroup test or the two-step subgroup test. Let's try it with the one-step subgroup test. Though remember, the one-step subgroup test is really a two-step subgroup test, and the two-step subgroup test is really a three-step subgroup test. Why? Because there's a 0th step to show the set is non-empty, kind of like the base case of an induction proof. Why is the stabilizer not empty? Can you tell me? What's the reason? What's one element in the stabilizer? It's supposed to be a trivial element. The identity, epsilon. But wait a minute, if we don't know what X is, what's epsilon? Epsilon is still the function that maps every element of X to itself. If we let epsilon be, I'm going to go ahead and state it here as part of the proof, but you wouldn't have to state it, what I'm about to say, as part of a proof if I put this on the test. Let epsilon from X to X be defined by the formula that it maps everything to itself. So this is a capital X here, and that's a lowercase x. Capital X is the set. Epsilon's got a formula. Map everything to itself is what this formula is saying to do. I'm not writing it in array or cycle notation because X may not be finite. I could write epsilon as 1 or something if my set X consisted of the first n positive integers. But I don't need to do that. In the more abstract setting, I should just emphasize it maps everything to itself. Then epsilon is the identity of G. It has to be, because G is a group of permutations, it has to have an identity, and that identity, if you think about it, has got to be this function. I'm not really fully proving this. I'm just sort of re-emphasizing this is something to know. And epsilon of A is equal to A, because A is an element of X. So epsilon is in the stabilizer of A, and that means the stabilizer of A is non-empty. Okay, that's the 0th step. Now let's do the one-step subgroup test after that point. Let alpha and beta be in the stabilizer. We must show that alpha beta inverse is also in the stabilizer of A. Assuming, in other words, alpha and beta map A to itself, it's got to be the case that alpha composed beta inverse maps A to itself. That's pretty trivial in terms of understanding functions. I'm not going to write any more sentences here for sake of time. This implies alpha of A equals A and beta of A equals A. And beta of A equaling A implies beta inverse of A equals A by the definition of an inverse function. And these two things together are going to imply alpha composed beta inverse of A, which by definition is alpha of beta inverse of A, is alpha of A, which is A. Done. It's actually pretty easy. Now, you may look at this, or I see you furiously writing and think this feels confusing. It's actually very, very simple. But realizing what you need to do and realizing this is what you need to do is still hard for people. By saying it's simple, I'm not saying it's easy. I'm saying once you understand it, it is easy, but it doesn't mean it's easy to understand it right away. This is the heart of what you need to do. Alpha and beta are in the stabilizer. They are functions that map A to itself. I can write that. Beta mapping A to itself means the inverse of beta maps A to itself. The inverse will exist because beta is a one-to-one and onto function. Compose alpha with beta inverse and plug in A. By definition of composition, you get that, and then use these facts to say alpha composed beta inverse of A is A. Therefore, alpha beta inverse is in the stabilizer, and that does it. Therefore, the stabilizer of A is a subgroup of G by the one-step subgroup test, which included a 0th step, so it really is 2 steps. We're done. Praise the Lord. Stabilizers are important. They're going to come up in chapter 7 as really related to an interesting application of group theory. Thinking about symmetries of three-dimensional objects, fairly simple three-dimensional objects, which has applications, for example, in physics. Crystallography, I think it's called. Crystals, like how do you understand crystals and their structure, their molecular structure? Physics/chemistry application.